Yeah, it's a big pleasure to introduce Irina Limonova, who is a member of the lab High Dimensional Approximation at the Moscow State University, Lomonosov University, in the group of Vladimir Temyakov. And yeah, she's going to report on her results on sampling discretization in L2. So please.
Thank you. Good morning, everybody. Let me thank you, the organizers to give an opportunity to give this talk. And this talk is based on the joint work with Professor Temyakov. We consider the problem of discretization of L2 norms of functions in a given finite dimensional subspaces. We start today with the case of discretization with equal weights. In this case, we really need to impose some assumptions on our subspace to have a good discretization. Next, we will turn to the weighted discretization, and it's really good case because in this case, we have a good discretization for any subspace that you can imagine, finite dimensional. And at the end of my talk, I am going to tell you a few words about proofs. I would like to mention that I need to repeat some definitions and theorems from our talks of this week for the completeness. Okay. Omega for us will be a non-empty subset arbitrary of Rd with the probability measure mu. We say that a linear subspace Xn admits the Marcinkiewicz type discretization theorem with some parameters and some constants C1 and C2 if there exists m points psi j in omega such that for any function of this subspace they have this two-sided inequality. We can think about it as we replace the measure mu by a discrete uniform measure with support on this set psi j. And this will be, these inequalities will be, will say us that the norms in LQ with respect to measure mu and with respect to uniform discrete measure are equivalent. Professor Temyakov has already said that this condition E plays a crucial role in the case of equal weights. We say that an orthonormal system Ui of x defined on omega satisfies condition E with a positive constant t if for all x they have the following inequality. We can integrate this inequality over all x, and then it turns out that t is greater than or equal to 1 because the L2 norm of each ui equals to 1 equals 1. We start here with the result of Rudolphson. It was really about the submatrices of orthogonal matrices, but we reformulated for our purposes. Let's have a look. We have omega m is a discrete set. This is a uniform probability measure on it, mu m. Assume that a real orthonormal system ui of x satisfies condition E on our discrete set. Then, for every epsilon greater than 0, there exists a set J of almost good cardinality. Excuse me, do you hear me now?
Yes. Yes, I hear you.
I have some strange words on my screen, so I ask, thank you for the answer. This almost good cardinality, such that for any f, in the space spanned by ui of x, we have this two-sided inequality. It is really Marcinkiewicz type discretization theorem, and I will call it a discrete one, discrete Marcinkiewicz type discretization theorem, because of this set is a discrete one. And if we see this theorem, a number of questions naturally arises here. The first question is about this word discrete. Is it really necessary here, or the analog of this theorem can be proved for a general set with the probability measure mu, not all uniform one? The second question concerns this cardinality. In most typical situations, of course, we, for good spaces, we have the necessary condition that m should be greater or equal to n. Can we remove this logarithm or not? The third question is about the word real. Is it true for complex orthonormal systems or not? And the fourth, more intriguing one maybe, about this condition. It is easy to show that they really need some conditions in the case of equal weights, but this condition might be very strong for our purposes. But I have nothing to say to this question. We don't know. Okay, let's have a look how we can answer other questions. The first successful attempt to answer the first question, which is about the word discrete, was given by Temlyakov in 2018. And this theorem states that if we have a real orthonormal system in L2 of omega mu, omega is a general set satisfying condition E, then for every epsilon, there exists a set of this cardinality of points psi j, such that we have the following inequalities. I would like to emphasize here that Temlyakov had done it in a different way than the Rudelson. It's another proof. And also, under the logarithm, we have here n, which is slightly better than n squared divided by epsilon squared. Okay, what about other questions I have posed? In 2017, Temlyakov proved the following theorem. Let omega m be a discrete set with the probability uniform measure on it, and assume that an orthonormal system satisfies this strong condition. It is not a condition E, it is a much stronger condition. At each point, we have that sum of modulus to the power 2 of ui of xj is equal to n. And under this very strong condition, but of course, this condition is satisfied for a lot of systems, Rademacher system or Walsh system and the others. But for those systems we know discretization results, and we are seeking for something else. In this, under these strong assumptions, we have the following result. We have m is less than or equal to C1 n points, which is of order n, such that we have this good discretization. Note that here we have not we cannot make these constants C2 and C3 to be closer to 1 as in the previous results. For every epsilon, we can go to 1 as closer as we would like, and here not. But this is really good discretization. The number of points of order of the dimension of a subspace. And what we have done in our paper is this theorem. Omega here is an arbitrary non-empty set with a probability measure mu, and they assume that our system, real or complex, is an orthonormal system in L2, and it satisfies condition E. Then we have a very good cardinality for the set of points needed for the Marcinkiewicz type discretization result. There are C1 T squared n points less than or equal to, and the T is from the condition E, such that they have two-sided inequalities. We can reformulate our theorem in terms of Nikolsky's inequality. Let's do it. Let Xn for convenience now be an n-dimensional subspace of real or complex subspace of continuous functions, C of omega. We say that Xn satisfies the Nikolsky inequality for the pair to infinity if there exists a constant T, positive constant such that they have this bound of a norm in L infinity, the superior norm. We point out that this condition, if we take Xn to be spanned by U1 etc. Un, where Ui is an orthonormal system, is equivalent to condition E. And it is easily seen from this proposition. This proposition is only the consequence of Cauchy's inequality. Let Xn be an n-dimensional subspace of C of omega. Then for any orthonormal basis of Xn, we have that for any point in omega, the supremum of this quotient equals to that sum which really appears in condition E. And so we get this result. Let omega be a non-empty compact set. This is the probability measure mu. Assume that it satisfies the Nikolsky inequality. Then, where exists a set of cardinality of order n, this is the property, our property. Okay. Now, I'll turn to the case of weight discretization. Very different case. What is that case? Instead of this sum, we consider now this sum where lambda j are the real numbers. I would like to mention that in our paper, these numbers are non-negative, but in some cases, we really need to have a negative one. The very first result in that direction, I mean the direction of finding a good cardinality for the points which we need to have a discretization, Marcinkiewicz type discretization with weights, is done in the paper of Batson, Spielman, and Srivastava in 2014. Let's have a look. Let omega m be a discrete set with a probability uniform measure on it, and Xn be an n-dimensional subspace of real functions defined on omega m. Then, for any number b greater than 1, where exists a set of non-negative weights such that the cardinality of non-zero weights is of order of n, and they have an explicit bound, so that for any f in Xn, we have this two-sided inequality. Can somebody prove this result, when we replace discrete set to the general one, yes. And as observed in the paper of Dai, Primak, Temrykov-Tikhonov, this last theorem with a general probability space in place of discrete space remains true if xn in L4. And this condition is unnecessary here, which is shown in the follow-up paper by Dai, Primak, Chadran, Temrykov-Tikhonov. And what this theorem says: if xn is n-dimensional subspace of the real L2 of omega mu, then for any b in the interval 1, 2, where exists a set of m less than integer part, low integer part of bn points, and a set of non-negative weights, such that they have these inequalities. Here are the constants a little bit worse than in the case of Batson, Spillman, and Srivastava, but the result is more general. And we established that this theorem, but not with such great constants, and as here or as in the previous theorem, holds for the case of complex space. If xn is an n-dimensional subspace of the complex L2, then there exist 3 absolute positive constants and a set of great order of points, psi 1, etc., psi m in omega, and a set of non-negative weights, such that they have these inequalities. At the end of my talk, I will give a remark how the theorem, the Marcinkiewicz type theorem in the real case, is connected to the Marcinkiewicz type discretization theorem in the complex case. And due to this remark, we have a slightly improvement or maybe explicitity of this theorem. We claim that this theorem holds with m is less than or equal to the lower integer part of 2bn, and c0 equals to 1, as in the previous theorems, and c0 prime capital is equal to the same constant as we had here. Okay, and now I'll turn to the third part of my talk, and this is about proofs. Our proof is based on very deep result by Marcus, Spillman, and Srivastava, which is really solved for 59-year state conjecture, Kadison-Zinger conjecture. Let's have a look. Let a system of vectors V1, such Vm from Cn, have the following properties. The first properties tells us that the system of vectors Ci's is the tight frame, and I will refer to it later. Also, we have this condition, and we also have a bound on the L2 norms of Vj. Then we can split these vectors into 2 parts, C S1 and S2, such that if we take all indices in one part, namely S1 or S2, it is almost 1/2 of this sum. Somebody also call it energy functional. This is almost 1/2 because epsilon is suggested to be small. Okay. Nitsan, Olevsky, and Ulanovsky proved this lemma, derived this lemma from the result of Marcus Spearman and Srivastava. If you have a system of vectors, which is a tight frame, and also these vectors have the same L2 norms, which are equal to square root of n divided by m, then there is a subset such that very good inequalities holds. Why are these inequalities very good? Because Professor Temlyakov remarked that for the cardinality of a subset J from this lemma, we really have that this cardinality is of order of n. And it is indeed the Marcinkiewicz type discretization, but under this strong assumption. And what we would like to do is to generalize and improve this lemma to be useful in our setting. This is the main lemma of our paper. Let a system of vectors V1 such Vm be a tight frame. And also we have not equality here, but we have that the norm of Vj to the power 2 is less than or equal to theta n divided by m. Then we can find a subset of a very good cardinality. For us, we assume that theta is a constant, which not depend on n or on m, but this lemma is also true if theta depends on it. But in this case, these bonds will depend on it, and it is not what we would like to have. Okay, we have a good set, a set of good cardinality, for which the Marcinkiewicz type discretization theorem holds, the discrete one. We can, this lemma really implies that the analog of this result in a weighted case. And I would like to show you how we can derive this corollary from the lemma. Let a system of vectors be a tight frame again, and we don't need any assumptions. We only can tell in this situation that there exists a set of non-negative weights such that the cardinality of non-zero weights is less than or equal to 2c1n, is of order of n, such that we have a good discretization with weights. How can we get it? Let's have a look. We choose the vector with the smallest L2 norm. Without loss of generality, we can assume that the norm of vector v1 is the minimum, is equals to a minimum of these norms. And for each vector vj, we built a vector with j prime, and also we built a system, new system of vectors, v1 prime, etc. vm prime all prime, in the following way. We include in Z nj's copies of the vector vj divided by square root of nj. What is nj? Nj, we obtain from these inequalities. For any number vj, norm of vj squared, we can find a natural number nj such that the following inequalities holds. And then of the system V, the condition E holds. And so we can apply the previous lemma. Okay. We can derive from this corollary in a very easy way the following discrete Marcinkiewicz type discretization theorem. What does it claim? Let omega m be a discrete set with a probability uniform measure on it. Assume that ui of x is an orthonormal system on omega m. Then there is an absolute constant C1 such that there exists a set of non-negative weights lambda j and a set of m of order of n points such that they have discretization theorem. I recall here the lemma for those who forgot it. And I would like to tell some words about the proof of this lemma. Really, we do have prepared ingredients for it. All was prepared for us. This proposition is due to Harvey and Olber, and also Nitsan, Olevsky, and Limonova. Let a system V1 such a Vm and delta is greater than 0 be such that the L2 norms are bounded by square root of delta. If they have these conditions, it means that Vi is not tight frame, but it can be frame, not tight. These some numbers, if we have this with some numbers, when we can split our set of with vectors into two parts, such that for each part, the following inequalities hold. If we have a tight frame from the beginning, in our lemma, we have tight frame, then we can apply this proposition. And the only thing to do is to control how these numbers change. And this can be controlled by this lemma due to Nitsan, Olevsky, and Ulanovsky. We have such numbers as defined exactly as in this proposition. And then these conditions give us a good cardinality if on every step we choose the subset of a smallest cardinality. I would like to emphasize here that this iterative procedure was firstly proposed by Lunin, and almost nobody do say here, it, not here. And we can derive this discrete Marcinkiewicz type discretization theorem from our lemma. If omega m and now with equal weights, because this lemma, it is something like equal weights. We have discrete set with the probability, uniform probability measure on it, and they assume that condition E holds for it. It is exactly condition E for a discrete set. Then there is an absolute constant C1 such that we can find a subset J of a good cardinality and have Marcinkiewicz type discretization theorem. Okay. And how we can derive a non-discrete theorem? And this ingredient was also prepared. it is in proposition by Dye, Primark, Temlyakov, and Tikhonov. Let's have a look. Let Yn be a subspace spanned by U1 of x, etc. Un of x, with Ui of x being a real or complex orthonormal on omega system, and assume that Ui, all Ui's, are in L4 of omega mu. Then, for any delta where exists a set, a discrete set, which belongs to omega, such that we can estimate the norm of any function in Yn by a discrete norm on this set. And this ingredient really works, and we can derive our non-discrete theorem. And almost the last thing I would like to tell you today is about this proposition. Let Xn be spanned by V1, etc. Vn, Wn, be a set of complex L2 of omega mu. And suppose that Wj equals to Uj plus I Vj. It's of course true, where Uj and Vj are real numbers or functions. We denote the subspace that's spanned by U1, etc. Un, and also V1, etc. Vn, but this subspace is a real subspace. We consider not complex weights, but real ones. Of course, this subset has the dimensionality is less than or equal to 2n, because these functions can be linearly dependent. Then, if the Marcinkiewicz type discretization theorem holds for Ys, these m points, then it's also true for Xn. Xn, in this case, admits the Marcinkiewicz type discretization theorem with also m points. And moreover, for discretization of Xn, we can use the same points and weights as for discretization of Ys. It is easy to show how we can derive it, and I would like to present it here. Take f in Xn and write f as a sum of fr plus ifi. These functions will be in Ys, which is spanned by u and z. And assume that we find, if Marcinkiewicz type discretization theorem holds for Ys, when we can find m points and m weights such that the following inequalities holds for any j in Ys. When we can easily bound this sum from above as here and from below in the same manner. This equals to this, and due to the fact that fr and fi belongs to Ys, then we have this inequality. And we can put it together to obtain the norm of f in L2 squared. This proposition also leads us to the improvement of the results which Professor Temlyakov had been talking 2 days ago about the sampling recovery, but it's not the subject of this talk. And here is the list of references I have mentioned in my talk. And thank you for your attention.
Thank you very much, Irina, for this nice talk. Are there any questions or comments? So the yellow hand, is that just an applause, or is it a, do you want to ask a question? Okay, maybe it was. Yeah, are there any questions? Maybe I have a question. So at the end of your talk, you managed this transfer mechanism from the real case to the complex case.
Yes.
And yeah, we also got interested in this Batson result since recently, because it provides this kind of deterministic algorithm, right? How to subsample the matrix and how to get this sparsification, to use Albert Cohen's notation, words. And we thought about like extending the Batson result to the complex case directly, and yeah, write it in this not tight frame way. And we are quite optimistic that this should work. So
it's very interesting.
I don't know if there is so far, I don't know if there is any thing hidden which does not, which proves me wrong. But I mean, then you could directly use that result also for the complex case, right?
Yes,
and,
of course, and have a constructive building of these points.
It's determinist, and the main advantage about this other thing, this more powerful result by Nitsanolevsky, Ulanovsky, and Markus Spielmann, Srivastava, is the much better constants, right? As you pointed out.
Yes, but due to this final result, we can have constants as in not in Nitsanolevsky, but in Dipro-Maksim-Likov-Tikhonov, as I'm not mistaken.
Excuse me, I didn't get the last comment. Could you speak a bit louder?
I speak that due to this proposition, we can have the same constants.
Yes, surely. Maybe
it's maybe I haven't mentioned that we have two different proofs of the weighted results, and this is interesting too.
Yeah, because I mean it should work, right? To maybe extend this Batson result. I don't know, but yeah. Are there further questions? Does not seem to be the case. So let's thank Irina again for her nice talk.